Welcome to lecture number 8. You may recall that in the earlier lecture, we had considered a model y I is equal to beta 0 plus beta 1 xi plus epsilon I goes from 1 to n, and we were trying to develop a test of hypothesis for h naught beta 1 is equal to beta 1 naught. And we had considered the case how to test the hypothesis when sigma square is known to us. Now we are going to assume that sigma square is unknown. Now if you try to see in practice, actually this situation is more important or say more applicable than the earlier case where we assumed that sigma square is known to us. We had considered that while doing the linear regression modeling, we have only a set of data on say xi and say yi, and we have to infer everything on the basis of that sample of data. When I say that sigma square is known, that means the value of sigma square has to be known from some past experience or from some other relevant sources. In real life, usually the value of sigma square is not known to us, and we need to estimate it from the sample. We had earlier discussed that we can estimate the value of sigma square by sum of square due to residual, that SSRS divided by n minus 2. Now we are going to consider here a situation which is more applicable in real life data set, where we have a set of data on say xi and yi, and we try to estimate all the parameters only from the data set, including beta 1 as well as sigma square, where we assume that expected value epsilon I is equal to 0 and variance of epsilon I is equal to sigma square. Right. So in this case, our next objective is how to find out test statistics. So we know that SSRS, that is the residual sum of squares divided by sigma square, follows a chi square with n minus 2 degrees of freedom. Right. And we also have seen that this beta 1 hat follows a normal distribution with mean beta 1 and variance sigma square upon Sxx. And we can also prove that these two are independently distributed. So now I can use a result from the statistical inference that if x is a random variable which is following a chi-square distribution and y is another random variable which is following a normal distribution, then y upon square root of x by n, this follows a t distribution. So in this case I can see here that this beta 1 hat is a normal random variable, this is following a chi-square random variable. So I can write down here beta 1 hat minus beta 1 0, which is known to us, divided by square root of sigma square hat upon Sxx. This follows a t distribution with n minus 2 degrees of freedom under h naught. Right. So this can be further written as say beta 1 hat minus beta 1 0 upon say SS res divided by n minus 2 Sxx. This is follows a t distribution with n minus 2 degrees of freedom under h naught. Because if you try to recall, we had estimated sigma square by SS res over n minus 2. Now this statistics we can denote by here say T1. Right. Now we try to see, depending on the nature of alternative hypothesis, we can have different types of decision rule. For example, if my alternative hypothesis is h naught beta 1 greater than beta 1 naught, then in this case, as we have done in the earlier case, this is the probability density function of t distribution with say here n minus 2 degrees of freedom, and this is going to be the critical region of size alpha, and this is going to be here acceptance region of size 1 minus alpha, and this is the critical value T alpha n minus 2. And this value T alpha n minus 2, this is obtained from the T tables, right. Okay. So, in this case I would say that reject H naught if T1 is greater than T alpha n minus 2, right. On the other hand, if my alternative hypothesis is H1 beta 1 less than beta 1 naught, where beta 1 naught is some known value, then in this case this T distribution will be like this, and the critical region will be on left hand side of size alpha, and this value will be minus T alpha n minus 2, and somewhere here will be 0, and in this case I would say that reject H naught if T1 is less than minus T alpha n minus 2, right. The third case will be of H1 beta 1 not equal to beta 1 naught, right. In this case again the T distribution will have critical region on both the sides of size alpha by 2 and alpha by 2, and this will be the value minus T alpha by 2 n minus 2, and this will be the value T alpha by 2 n minus 2. So, I can say here that reject H naught if absolute value of T1 is greater than T alpha by 2 n minus 2, right. So, this will again be our acceptance region of size 1 minus alpha. So, this is how we proceed to test the hypothesis about the H naught beta 1 is equal to beta 1 naught. Now, next question is what is the interpretation and what is the utility of making this test of hypothesis. So, let us try to understand the use. Okay. Now, when I am trying to test a hypothesis like H naught beta 1 is equal to beta 1 naught, and suppose beta 1 naught is equal to 0. So, essentially we are trying to now test a hypothesis beta 1 is equal to 0. Now, there are two options, either our H naught is accepted or not. So, in case if I say if H naught is accepted, then we say that beta 1 is equal to 0 at alpha level of significance on the basis of given sample of data, right. Now, what is the interpretation of this thing? We had learned earlier that beta 1 is the slope of the line. So, when I am saying that H naught beta 1 equal to 0 is accepted, that means the slope of the fitted line is 0. That means the fitted line is going to be something like this, and all the points which are scattered around this line will look like this. So, this means here what? This means the slope of the line is 0, that means x is not contributing in explaining the variation in y. Whatever happens here, either here or here or say here or say here, whatever the values x takes, there is no change in the value of y. So, what we can see here is the following: there is no change in the value of y when values of x change, right. This means x is not contributing in my model building. X1 is such a variable which is not helping us in explaining the variation in the value of y, right. The second situation can be like this, that suppose we have a data like this one which is really non-linear, right, and in this case when we are trying to fit here a linear model, this will look like this, right. So, what does this mean? That means there exists some relationship which is actually non-linear, and our x is trying to help the variation, but still it is not capable of explaining the variation. So, in this case I can say here in simple words, the true relationship between x and y is not linear, right. In either of the case, h naught beta 1 equal to 0 is indicating the true situation. When the relationship between x and y is non-linear, why should we fit a linear model? Well, in this case, in case if somebody wants to proceed, then we have a setup of polynomial regression model that can be used. So, now we can see here, once beta 1 h naught beta 1 equal to 0 is accepted, then in that case our model now becomes, say, y is equal to beta 0 plus beta 1, which takes actually value here 0 into x plus here epsilon. So, this quantity becomes equal to 0. So, this implies that x is not contributing in explaining the variation in y. On the other hand, there can be another situation that suppose h naught beta 1 equal to 0 is rejected. So, what are we trying to say? We are simply trying to say that in this two-dimensional graph x and y axis, yes, there are some observations like this, and we are trying to fit here a model like this one. That makes sense, right. That means x is helping in explaining the variation in y, or in simple words, this implies that a straight line model is adequate, and that is essentially what we wanted. Okay. On the other hand, if I try to take the second case over here, where we had a non-linear relationship like with this one, and suppose even if we are trying to fit here a linear model, this may look like this, right. Even in this case, we can see here that as x is changing, the values of y's are changing, but that is possibly indicating a non-linear relationship. So, it is suggested that by considering a polynomial regression model of say higher order like 2 or 3, that may work in this situation. So, this is about the test of hypothesis using the classical approach. Now, there is another issue. Usually when we do this regression modeling, we try to use a statistical software, and nowadays statistical software gives us the outcome about the test of hypothesis using another criteria, what is called as p-value approach. So, here I would like to explain you that what is this p-value in case if you are working with the software, and how to interpret it, right. So, statistical software provide p-values, and in this case we do not look on the critical region, but we simply try to look on the p-value, and based on that we try to take a decision whether my null hypothesis is accepted or not, right. This p-value is nothing but this is the estimated probability of rejecting the null hypothesis. Right. So, in simple words, if I say if Tx is my test statistic, which is, for example, in case of testing H naught beta 1 equal to beta 1 naught, when we know the value of sigma square, then Tx is nothing but z, and in case if sigma square is unknown to us, we try to estimate it from the sample, and then we use the T statistics. Right. So, in this case, the p value is defined as for one-sided hypothesis, this is defined as probability under H naught that T is greater than some given value small tx. Right. This is for the right tail tests. And in case if I am considering a left tail test, then this is the probability under H naught T less than Tx. So, we are simply trying to compute the probability of T being greater than the given value Tx or smaller than Tx under H naught, that means when H naught is true. Right. And when I have a two-sided hypothesis, then this is defined as probability under H naught absolute value of T is greater than say Tx. Right, because for us so. Now, the software will give us this value, and that is simply given by so called p value. Now, what is the decision rule? If p value is smaller than the significance level, which we had denoted as say here alpha, then the null hypothesis, which we have denoted by H naught, is rejected. Right. So, this gives us a very simple solution. Just look at the software, try to look at the p value, and whenever we are doing the modeling and consequently we are doing the test of hypothesis, we have to define the level of significance. Usually it is 5% or 1% depending on the situation. So, alpha is equal to 0.05 or say 0.01 depending on whether we are using 5% level of significance or 1% level of significance. So, you simply try to compare the p value and the value of alpha, and based on that we can take a correct decision about the test of hypothesis. And this approach we need not to look into the tables of either normal probability or say T probability. So, that is the advantage of this approach. So, okay, you stop here now, and I would request all of you to just have a close look whatever we have covered in this lecture and the earlier lecture, and try to understand how we have constructed the test statistics and how we are going to use it. Now, our next objective will be first of all to develop the test statistics for testing of hypothesis for the intercept term and for the sigma square, and after that we will concentrate on the confidence interval estimation of all these parameters. Till then, goodbye.